guess we are live. So welcome everybody. Thank you very much for coming. Thank you very much for attending. Yeah, you can see my screen now. Awesome. Okay, so what we are going to try to do today, we are going to do some live coding. We'll see what breaks and we'll see what works. We will try to implement something that's, I think, quite common in like our everyday jobs. So we won't go crazy. It will be rather basic stuff, but still we will try to use a novel approach. Maybe not so novel, but maybe also, not mainstream, definitely distinct from what you would see in a typical Java, Kotlin, .NET application. So we will try to use functional programming. And the problem that we will try to address is how to interact with WebSockets, how to expose WebSockets on the server, and how to interact with WebSockets on the client side. So our quest will be, well, first of all, as you can see, to use a lot of different libraries. So we will use HTTP4S, CATS-effect, tapir, FS2, Async API, Zio, sttp. Some of them we will use on the server, some of them we will use on the client. And probably from the number of libraries that we are going to use, well, it can be quite scary. But the goal, my goal here is not, to teach you in any way the details of the APIs of these libraries, or to show you, it's not the goal so that you can write your own applications using these libraries. They all have quite good documentation. There's a lot of blog posts out there which you can actually use to learn. Instead, what I would like to convey is a general feeling of how is it like to write an application, a normal everyday application using the functional approach. So we will try to implement a WebSocket server using functional programming, using streaming. We will try to generate some documentation, and we will try to implement a WebSocket client. And we will see how that goes. So there's going to be a general theme why we will be coding, and I hope you will see some of these elements that I will talk about here while we write down the code. So the general focus is going to be that we will try to describe solutions to the various problems that you encounter, such as exposing a server, defining the endpoints, and so on. We'll try to describe these solutions using data structures. Our programming languages, and especially Scala, is really good at manipulating data, right? We create like a case class is like the most basic building block of Scala, you could say, right? It's so common and so useful that we use it every day. We put them in collections, these case classes, right? And we manipulate them, we create copies, and so on and so on. So we are used to doing that with like business data. And here we will try to do the same with more technical aspects of our application. So once we have those descriptions, we will then interpret these data structures in various ways and hopefully get some profit out of it. So before we actually start to code, just a short introduction of who I actually am and why would I be a good person to talk about this subject. So I actually counted, and it turns out it's already 15 years since I've started doing backend programming commercially. I started with J2E. I had an episode with Spring. Then I moved on to Scala, and I've actually did Scala professionally longer than I did Java since a couple of years. So I did Lift, some Akka, and then moved to the more functional aspects using HTTP4S, Monix, CATS, Zio, and so on. And day to day, I'm a programmer, software engineer, and the CTO at Software Mill. We are a company which is doing custom software, distributed systems, big data, fast data, sometimes slow data, machine learning, blockchain, messaging, and so on. All of whatever is currently most popular, of course. We're also doing some Scala, Kafka, and Cassandra consulting, and I'm personally also involved in a number of open source projects such as sttp, tapir, Macquarie, which maybe you've encountered or maybe which you will encounter. We also write a lot on our blog, so if you like technical articles, that's the place to go. Okay, so let's start. Let's start on the server side. So what is our example application going to be? So we will implement a very simple Fibonacci game. So the goal here is that the client, the player, will connect to a server using a WebSocket. Upon connection, the server will return two numbers, and the task of the player is to return the sum of the last two numbers for the specified number of rounds. So the more rounds, the more difficult the game is, right? So we return the sum of the first two numbers received from the server. Then we have to return the sum of the, again, last two numbers, and so on until we lose or win. So on the server side, we have to accept client connections and return these initial two numbers, and then check if the incoming guesses are correct. So we will expose a single endpoint, so this is going to be quite a simple application. And to expose the endpoint, we will use the tapir library and the HTTP4S server. So the tapir library is used to describe endpoints using a data structure. So we will capture our WebSocket endpoint as a data structure. So we will create a value, Fibonacci game endpoint, and that value will capture the structure of the endpoint that we want to expose. So to capture the structure, Tapir gives us an API. The starting point of any endpoint definition is an empty endpoint, right? So we start with an empty endpoint. That value is defined in the Tapir library. And when defining an endpoint, we incrementally define more constraints. We specify what are the inputs of the endpoint and what are the outputs of the endpoint. The inputs of the endpoint is whatever the endpoint reads from the request, and the outputs are whatever the endpoint writes to the response. So in our case, we start with an empty endpoint which has no constraints whatsoever, and we specify that as that is going to be a get endpoint. On the input, we want to accept requests on the fib path, right? Maybe we also want to have a query parameter which specifies the difficulty of the game. So we will accept on the input a query parameter which is going to be serialized to an integer value, and the name of the parameter is going to be difficulty. Yeah. Okay, now what about the output? In case of an error, we will return a string body. And in the case of success, we will return a WebSocket body, and we need to provide some more details here. So each of those methods, the .in, .errorout, and .out.get, each of those methods adds a new constraint on the endpoint, specifies a part of what's being read from the request or what's being written to the response. So each time we call them, we get a new data structure which describes a bit richer endpoint. This data structure is readable, so any modification actually builds upon the previous one, but the previous one is left, of course, untouched. Okay, so now we need to specify the WebSocket body. We can work with WebSockets on two levels. On the low level, dealing with WebSocket frames. A WebSocket frame can be textual or binary, or we can work on a higher level, specifying what is the protocol expressed as case classes. So here our protocol will be JSON-based. We will accept some messages as JSON, and we will send messages as JSON as well. So the protocol is specified in the FibGame file over here. That is these are the messages that we will accept from the client. So our clients will send guess messages to the server. These messages will be serialized. Well, they should be serialized as JSON, but we will deserialize them into the following case class. So there's only a single message that the player ever sends to the server. The response is a bit more interesting. So we have 3 possible responses. The server can send a start message to the player or a lost or won message, right? So it's a C straight. So the response is one of these 3 possibilities. So let's go back to our endpoint definition. So here we can specify that our WebSocket body, we will use the higher level representation, and the request part should be deserialized to a guess class, and it should be formatted as JSON, and our responses should be deserialized to the should be serialized as the response class, and also formatted as JSON. So these classes over here are exactly the same as we had over here. By specifying the class, the model class over here in the format, we also summon from the environment an implicit parameter, which is a codec, which knows how to encode a guess case class into JSON, right? So here we are using Circe behind the scenes to actually do the serializing. Everything is automatically derived, but if you would like to derive it, if you would like to specify it by hand, this is also possible. So these type of parameters define one implicit codec, and these define a second implicit codec. One more thing that we need to specify here, a WebSocket body, in fact, defines a streaming body. So adding a body like this adds a constraint that the response body will be a stream. So here the stream will convert a stream of incoming guesses into a stream of outgoing responses. So we need to provide the specific streaming implementation that we are going to use. We can choose from Akka, FS2, Zio streams. Here we are going to use FS2 streams. Okay, so now our description is complete. We can take a look at what is the type of the value that we have created. Okay, maybe this will be more readable. You can see that the type here is an endpoint. If we go to the definition of the endpoint, you can see that it is a case class, so a data structure, as I mentioned. This data structure has a couple of type parameters. So the first type parameter are the values that we extract from the request. The second are the responses in case of an error. And the third is a response in case of success. So here it is a pipe. A pipe is a transformation of a stream of guesses into a stream of responses. Great. So now we have the description, the structure of the endpoint, but we haven't yet implemented the logic. So to do that, we need to define another value, Fibonacci game server endpoint. So we take that endpoint that we have defined over here, and we will couple it with the server logic. So the server logic, as you can see, it is a function. So the function that we have to provide, it takes an integer. So this corresponds to whatever we read from the request. Here it's a single integer. It can be also multiple things. And we have to either return an error as a string or a success, which is an implementation of the WebSocket logic, right? So here our function will take in the difficulty, and we will now implement the logic in the other file. So we will just reference it here. And difficulty, and we won't actually do any validation over here. We will just always return values as we will always return success. So we always return the right from the either. Okay, so now let's actually implement the logic. So here we have the structure of the endpoint. Here we have the endpoint coupled with the server logic, but we still need to implement the logic. So let's go to that file. We have the protocol over here. So how will we implement the logic? Well, we will need to keep some game state, right? We will represent our game state as a case class state. It will hold 2 numbers, the current 2 numbers that should be added by the player, and the iteration number, which is an integer. We will also add a way to convert the current game state to the start message, which we want to send to the player. Another thing that we need is we need to create a new game state, right? We need to somehow initialize the game. So we will create a value which describes how we can create a new game. So next game will be our value. It will be an IO of state. So what is that IO of state? IO, it is well, an IO monad. It is a data structure which captures some computation which can possibly have side effects and which computes a value of type state, right? Which is what is important here is that it is a description. So just creating that value doesn't actually run any side effects. It just describes what we need to do to compute that value. So what we need to do to compute a new state. So first we randomize the second number, random next integer 10 plus 1. Then we randomize the first number, which will be smaller than the second number. And we yield a new state, which is n1, n2, and the iteration number is 1. Okay, so what we do here we have a side affecting computation, but we don't run it. We create an IO, so we create a description of which, when evaluated, will actually run this side effect, which is captured inside that constructor call, right? So this is a value, this is an immutable value which describes our side effect. Okay, so now we have to actually create the stream that will implement the business logic. So we define an apply method with a difficulty that's being passed in from the query parameter. And what we have to return is an IO pipe, IO guess response. So we are returning a pipe, but to define the pipe, to create the pipe, we might have to run some side effects, right? So this type signature says that what we are returning is a description of a side effect, which when evaluated will return us a pipe. And that pipe can convert a stream of guesses into a stream of responses. But when the conversion actually, like when the stream is actually run, IO side effects might happen again, right? So that's the same IO. And the side effects here might be, for example, reading from the WebSocket or writing back to the WebSocket. Okay, so what we do here is we first initialize the game, initial state, next game. And so we have the initial state, and that is the side effect, right? That is the side effect that is happening over here. So what we do now, we take in this incoming stream input. It's a stream IO guess, right? Input. So the pipe over here, if you actually go to the definition of a pipe that the streaming transformation, you can see that it's simply an alias for a function which takes the input stream and produces the output stream. So that's a pipe. So here what we do is we take the input stream and now we have to produce the output stream. Well, on the output stream, the first thing that we have to do upon connection is send the start message. So we create a stream with a single start message created from the initial state. Okay, so that's the initial start message, and then we have to somehow react on the incoming guesses, right? So we take the input, well, and we have to somehow we need to take the guesses as they come in one by one, and we have to somehow accumulate them, right? We have to accumulate the user guesses into the state and produce, maybe they won, maybe they lost, or maybe we wait for the next guess. So there's a number of combinators in FS2. By the way, an important detail which I missed, the pipe, the stream, these abstractions come from FS2, which is a streaming library for Scala. And we are using here, the IO data type comes from Katz effect. And as you can see, Katz effect and FS2 work very nicely with each other. So they form a very cohesive ecosystem. So what we need to do here is we take the input stream of guesses, and we call one of the combinators that's available, eval map accumulate. You can see the accumulate work here, so you can guess that there's some accumulation that's going to happen. The type signature confirms that. So the type signature is that we need to provide an initial state of the accumulation. So that's going to be initial state. And then we need to provide a function which takes the current state and takes the incoming guess. And what we have to produce is the next state and possibly some output messages, right? So this function allows us to implement a stateful transformation of streams where we have some initial state and we build upon that initial state, producing some output messages and consuming whatever comes in this stream. Okay, so what we need to do here? Well, we first need to check if the guess is correct or not. So we will create a response value. So now if the guess.number is equal to state.n1 plus state.n2, so that is a correct guess. If that's a correct guess, we have to check if the user didn't win. So if the number of iteration is equal to the difficulty, then we return a won message, difficulty. Otherwise, we don't return any message. We'll wait for the next one, right? Because that's the normal state. We don't respond with anything. The game hasn't ended. Now, otherwise, if the guess is not correct, well, then the user lost, unfortunately. So we have to return a lost message that we have expected n1 plus n2, but we got number, which is incorrect. So yeah, well, addition is not always that easy. So now we have an optional response. If the response is defined, it means that the user either won or lost, right? So then we have to send the won or lost message and start a new game. Otherwise, we don't really do anything. So we match here on the response. If there is no response, we just return we have to compute the new state. New state that we are going to return is going to be the old state, but the second number becomes the first number, and the second number is state.n1 plus state.n2. Or the guess number we can just use. We can just use the user's guess over here, right? Because it was correct. And we increase the iteration number. Okay, and we return a new state and an empty list of response messages because we are waiting for more guesses. Okay, now if there is a response, well, then we always need to create a new game, regardless if it's won or lost. So we create the new game effect, and here we need to return a pure value because we need to provide, so the eval-map accumulate needs to return a function which can potentially contain side effects. Here we just return a value without any side effects. Hence the .pure. Okay, so in case we have a response, the user won or lost, we start a new game, and that's the new state that we want to return, the new game state. So we return the new state and a list of 2 responses that we want to send to the user. We want to send first the result of the old game, and then a new start message created from the new state. And that's it. We've defined the logic of our game. One more detail that we have still to do is here. So this transformation will actually return tuples of state and output messages. We don't care about the state. So you can see here that on the output of the stream, we get a state and the list of responses. So we discard the state, and we just take in the list of responses by taking the second tuple element. And then we have to also flatten the list of responses into a stream so that we get a stream of responses, not a stream of list of responses. So these are just technical details. Okay, but the Scala compiler is here to check that we actually do what we were supposed to do, and it guards that the types are correct. You can see that there's no red code, which is always nice. Okay, so now that we have the logic implemented, we can actually go back to the game server. In the game server, you can see that, yeah, this is now this is now compiling. So as the server logic, we pass in the function that we have just written down, which implements the transformation of the stream. So one more thing that's missing is we need to somehow expose our endpoint to the outside world. So we have created a description of an endpoint, which describes the structure. We have the server logic. Now we need to convert it somehow to something that's exposable outside. So for that, we have to actually expose the server. We will use http4s, which is a Scala library, a Scala HTTP server. But to be able to use http4s, we need to interpret what we have created over here into some form that http4s actually understands, right? So because here we have used the tapir API to describe the endpoint, but we need to have something that http4s understands. So we need a function which converts tapir things into http4s things. That function is called http4s server interpreter, and we just need to call the route dot, not comma, to routes method on it, fib game server endpoint, and we can assign it to the fib game server routes. Type here is http routes.io. Okay, http routes.io, as you can see, this comes from http4s. So now these routes, we can expose them to the outside world. And I have the exposing part already written down here, this thing here. It's not that interesting. There are some implicits that you need, which define the thread pool on which the connections are handled. You need to specify the port. And here's actually the most interesting part where we specify the routes that the server should expose. And that's more or less it for the server part. One more thing that we might do is we might want to add some validation to our query parameter. Right now we can pass in like -1 and it will work, but that's probably not what we want to do. So we could probably enhance the description that we have created with some validation. So what we might do here, this thing over here, this method query returns a value which describes a query parameter. So you can take that value and extract it as a top-level definition, difficulty input, and then we can use it in our endpoint, or we can use it in multiple endpoints. And we can say that we want to validate that the minimum validator.min is 1 and it's exclusive true. So it's at least 2, and an example value would be 2, and we can provide a description of our query parameter. How many rounds, how many numbers to provide doing, right? And each input, each output that we use can be described in this way by providing validation, examples, various pieces of metadata. Okay, so that's the server. Let's actually try and run it, and then we will move over to the client. I hope it will compile or not. So for the client, one possibility for the client that we might do, uninitialized field. Cool. Context shift. Maybe I should do it this way. Because the two routes actually uses this value. So the order was incorrect. But at least you can see that it's actually compiling the code that I write. Okay, the server is started. So one way in which we could write the client is we could take the description of the endpoint that we have over here and use another interpreter to interpret it as a client and make client calls against the result of that interpretation. That is one possibility. We are not going to do it here, but it's perfectly fine. We are going to take another approach, a more low-level approach. So what we are going to do is we are going to use the STTP client together with the Zio library. And we are going to use a slightly lower level interface. So we are going to operate on the level of WebSocket frames. I think it's quite common that clients, maybe if you have a simple WebSocket protocol, just operating with WebSocket frames might be good enough. So that's what we are going to do here. So once again, what we will do is we will create a description of the request that we want to send. So let's say on the client side that I will want to have a difficulty of 3. So I will create a description of the request that I want to send. Once again, here we are using the sttp client library to describe the request. So we are starting with an empty request, which doesn't really specify anything. It doesn't even have the URI. So I start with an empty basic request, no headers, no anything. And I say that I want to do a get to the following address, WebSocket local host 8080. And we are going to request the fib path, and the difficulty, it's a hard word, is going to be, we are going to embed whatever the value of the parameter over here. So you may have seen in Scala the string interpolator. So here we have the URI interpolator, which is very similar. It creates the URI with values embedded inside it. But the embedding is smart, it's contextual. So if there would be a value that would need some escaping, this would be done for you. So we need some more details over here to describe our request. We also need to specify that we want to handle the response as a WebSocket, and the as WebSocket actually needs to be provided with a function which takes a WebSocket interface, what it is I will say in a second, and performs some side effects. So this will be the play function that we will specify over here. So let's write down this play function. Our play function will take a WebSocket, which is of type WebSocket. That's again coming from sttp client. I will explain the type parameter in a second. Console star, and that's array console unit. Okay, so what is the WebSocket over here? This WebSocket is a very simple interface for interacting with the WebSocket in a much more imperative way than we've seen before. So on the server side, we've done a very declarative type of description of how we want the stream to behave. Here we can interact with the WebSocket imperatively by running send and receive methods, right? So when we invoke WebSocket.sendText, it will actually create a description of a side effect which will result, when evaluated, will result in sending the given text to the WebSocket. So the side effect container that we are using here is a bit different. So we were using IO from Cat's effect. Here we are using something else, which is called Zio. And the basics are very similar. If we go to the definition over here, you can see that the Zio data type has a couple more type parameters. So the first type parameter specifies the environment. So these are the dependencies that we might use. The second type parameter specifies the possible errors that might occur when evaluating our function. And the third is the result type. So here we are going to use a single dependency, which is the console. So let's use it. So the first thing that we do is we will create a description of a side effect which will receive and handle a single WebSocket message. Receive 1. So we call receive text on our WebSocket, and then we flat map it. And what we want to do with the result is we just want to print it to the console. So we call the put string line method received t. So this method comes from Zio, and it describes an effect of writing something to the console, right? So that's where we are using the console dependency over here. Okay, so that's a description of how to handle a single, how to receive and handle a single WebSocket message. In a similar way, we will describe the effect of sending a single message. So here we need to do 3 steps in sequence. So first we print a prompt to the user, next guess. Then we read a line of text. And finally, the third step that we need to do is we need to send some text to the WebSocket. We will do handwritten, hand serialized JSON because that's a simple client. It doesn't have any JSON library. And our guess will be G, right? And we just use a unit. Okay, so we have those two side effects. So now what we want to do is, let's take a look at the receiving side. We want to take the receiving effect and we want to run it forever, right? We want to, for every incoming message, we want to print it to the console. So we write receive1.forever. This describes an effect of evaluating this receive1 effect over and over again. In a similar way, we want to run send1 also forever, right? So we have those two descriptions, and now what we want to do is we want to actually put them together so that they are evaluated concurrently. We want to concurrently receive messages, and whenever the user decides and calculates the answer, we want to send the guess. So what we need to do is we need to describe a side effect, which we need to describe a side effect which runs those two in parallel concurrently. Okay, so what we do is we call .trace over here. So what .trace does is it runs these two effects concurrently until either one completes. It then interrupts the other one. Here, neither of these will complete normally unless there's some exception, like a broken network connection. Then when one completes, the other one will be interrupted, and that's exactly what we want. Okay, so we have described our request that we want to send. We have described the interaction that we want to perform with the WebSocket. Now we need to actually send things. So what we will do is we'll use the send method. The send method comes from integration between sttp and Zio, and what it does is describes the effect of sending a request. It describes this effect as a Zio value, so you can see that here the result is something that has two dependencies, is an effect with two dependencies. One is an STTP client and one is a console. The STTP client dependency is something that we need to provide. So we provide custom layer. Provide custom layer is like providing a dependency to the effect. So here we create HTTP client Zio backend.layer. So the dependency over here, what it does is HTTP client is something that's inside Java 11. It's an HTTP client in Java. So what we need to do is we need to actually provide the interface that, so in this application, we want to use the Java HTTP client. The HTTP client is where all of the threading is done, all of the network interactions, the serialization, and so on and so on. So that's where the heavy lifting is done. We are just providing a hopefully nice API for that. Okay, provide custom layer, and then we just discard errors. In case of an error, we just return exit code 1. Okay, let's see if that works. So let's run the code. And okay, we received the first prompt. 10 and 10. Let's say it's 20. Okay, and then 30. Okay, and now 30 plus 20 is 50. Great, we won, right? So we received the one message, and then we received immediately the next game that is going to start. So let's now try to lose. So maybe 1 plus 2, well, that's 3. Okay, that's easy. 3 plus 2, well, maybe that's 7. It's not, right? So we got a lost message as expected. And now we can play one more time. So that's the client. One more thing that I wanted to show you is another way in which we can leverage the description of the endpoint that we have created. So if we go back to the server, right, here we had the description of the endpoint that we have exposed to the outside world. So what we could do is we can actually take the description of that endpoint and render it as nice documentation. So Async API is a standard for describing APIs which have a streaming component like WebSockets, Kafka, messaging, Rabbit, and so on. It's like a counterpart to OpenAPI or Swagger, which you might know. OpenAPI and Swagger are for REST APIs. Async API is for streaming APIs. So here we have a streaming API, and what we can do using this interpreter, this function, we can convert the description of the endpoint into YAML, which is the documentation. So what we can do is we can actually run this. Function. What we get back is a long YAML, which we can now copy, and we can open up the playground. But I need to click the link over here. So we can open the playground, and I can paste in the YAML that was just generated, and you can see here that it contains all of the details that we have specified, right? So there's a publish operation on the path that we have specified. The payload is what we have defined. There's some more details about the query parameter that we have defined, which is the difficulty. It's an integer, it's minimum 1, and so on. Same with the receiving side. You can see here that it's one of 3 possibilities, right? So our type safe description that we have created in Scala is converted into YAML, which you can share with other people. So I guess it's a nice feature of the whole approach. Okay, so summing up, you might wonder, well, there's a lot of libraries, and maybe it's nice, maybe it's not so nice, I don't know. But where actually is the functional programming over here, right? So well, we have seen a number of data structures. We have created a number of data structures, but we have also used a number of functions to manipulate those data structures, right? The tapir API for describing endpoints, the FS2 API for describing streams, the way we capture and create side effects, the interpreters, right? The HTTPS interpreter, the Async API interpreter, the way we describe, the way we send, the send function in the client, for example, over here, right? This is a function which takes a data structure and creates another data structure which describes the process of sending an HTTP request, right? And also in the end, right, what we do here is we return a description of an effect. Returning this description in itself wouldn't do anything. It would just allocate some memory. We still need to have a function which actually interprets this IO, be it ZIO, be it CATS effect. We need a function which actually interprets it and actually performs these side effects, right? And this is done because we are extending the ZIO app. So the ZIO app requires you to define the run method, which returns the side effect, and then it actually evaluates those side effects as specified. And that's where the function programming is, right? Functional programming in its essence is just functions which take data structures and they produce more data structures, or they produce more functions, and these data structures contain functions. So, you don't need monads or anything like that to do functional programming. You just need the data and you just need functions. And, Scala is the perfect language to actually do that with the most basic building blocks, which are case classes, and the flexibility and scalability in which you can actually define functions, right? And throughout the way, we have seen how we separate the description of our problem from the interpretation of the problem in various scenarios. And because of this indirection, we actually got a lot more flexibility. So to sum up, some things that I think are worth taking a look at. The declarative explicit concurrency, this was especially visible in the client side. So for example, if we go back over here, that's where we have concurrency, right? That's why we specify 2 concurrently running processes. And because concurrency is hard, it's good to have a nice API which hides as much unnecessary detail as possible, but it is also good to actually be explicit about where you are concurrent. And I think this code is, because it is explicit and because concurrency is hard, is also quite readable, and it's also quite easy to understand what is happening, right? You can exactly pinpoint the place where the concurrency, concurrently running processes are initiated, and that is over here, where when the race is invoked, right? Well, it creates a description of how to race, but that's where, if you are wondering where the concurrency points are in your application, this is where. We have seen a couple of APIs for performing type safe, for creating type safe descriptions of HTTP endpoints. requests, of creating streams and computations. Again, I think a very nice property, if we go back over here, for example, even if you are not familiar with the Scala, if you're not familiar with the tapir library, if you read this code over here, I think it's not that hard to actually understand that this is describing an HTTP endpoint and what are the components of this HTTP endpoint. So I think this code is quite readable. I might be biased, of course, but I think even for a newcomer, this might be quite easy to understand. And I think that's a very important property, that we keep our code as readable as possible. We've seen a number of interpreters, side effects, HTTP servers, and so on. And I hope I managed to convey a bit the general technique of separating the description from the interpretation of the solutions. So a couple of links. The code for this presentation is on GitHub. If you would like to load it in your IDE, try to break it, go ahead. There's a blog post with a couple more details and a bit more complex example, which also implements a client and a WebSocket client and a WebSocket server. The libraries that we've used, they have really good documentation. So if you're interested in those, take a look over there. As far as Cats Effect goes and Zio goes, there are also books which you can read. And finally, if you would be interested in Scala news, take a look at Scala Times. It's our weekly newsletter that we are running for 5 years now, I think. And it's out every week with a bunch of Scala news. If you have any questions, follow me or ask me on Twitter. My DMs are open. So with that, I thank you very much. And I guess we'll have a couple of questions now. Thank you. Okay.
Hi, Adam.
Hello.
Thanks for your presentation. It was wonderful. It looks like we have a few questions, and I'd like to answer a couple of them live on stage.
Sure.
The first question is it possible to expose that YAML-based documentation on the same server that's running the app at some point?
Yes, of course it is. So you can define an endpoint either using tapir or using your favorite HTTP library that, when a request arrives at the endpoint, you just return the documentation YAML. There are also in tapir, there are some modules which allow you to expose the Swagger UI together with the YAML. So in the case of Swagger, and it's as easy as adding a dependency and a specific route. So yes, it is possible.
Great, thank you. The other question we have for you live is, does the implementation of the server limit the HTTP backends we can use to expose the endpoints? For example, using Cats Effect prevents using akka HTTP.
Yes, at least currently, there is this limitation. So if you are using, if in the server logic, so we've defined the description of the endpoint, then we couple it with the server logic, and the server logic usually uses a very specific effect type. So it either uses an IO, or uses Zio, or it uses future, right? And this dictates which interpreters you can use. So each interpreter has a set of capabilities which it supports. So capabilities include WebSocket support, they include the effects that an interpreter supports, and it includes the streams. So the akka interpreter supports futures, akka streams, and WebSockets. The HTTP4S interpreter supports any effect implementing the Cats Effect type classes, WebSockets, and FS2 streams. The play interpreter supports some else combination, and there's a couple of other interpreters as well. So currently, if you're using futures, you have to use one of the future enable interpreters. However, I think there's nothing that would prevent you from writing an interpreter which would be like a decorator on another one, which would allow you to expose routes which use IO, for example, on an akka server. So it might be some glue code that you need to write, But in principle, there's nothing that would prevent it from happening.
Great. Well, thank you.
And coding.
Yeah, this concludes our live portion of the Q&A. There are a few more questions in that stage Q&A area. If you don't mind, go ahead and take a look, answer in text, and if you could share those links that were in the final bit of your presentation in the stage chat maybe, or even in response to one of the questions, be super fantastic.
Yeah, I'll hop in.
Thanks so much.
Okay, thank
you.
All
right. Thank
Have a
you.
good day.